There is a well in Mecca that has been drawing water for approximately 3,500 to 4,000 years. And when modern scientists finally tested it properly, several of what they found did not fit the standard models they expected to apply. This is not a video about miracles, and it is not a video dismissing the science. It is a video about what the verified findings actually show, what they do not show, and where the genuine scientific uncertainty still sits. The Zamzam well is located inside the Masjid al-Haram mosque complex in Mecca, Saudi Arabia, approximately 20 meters east of the Kaaba. One of the most visited and most religiously significant sites on Earth for the world's approximately 1.8 billion Muslims. The physical structure of the well is approximately 30.5 meters deep, about 100 feet, with the upper 12.8 meters passing through alluvial deposits of the Wadi Ibrahim, the valley in which Mecca sits, and the lower sections penetrating the volcanic basement rock typical of the Hejaz region of Western Arabia. The main water-bearing zone is a joint, a fracture, in that bedrock at approximately 13 meters depth, where the majority of the water flow enters from the surrounding rock formations, with additional smaller water-bearing zones at greater depths. Modern Saudi authorities have installed electric pumps with a capacity of approximately 8,000 liters per second for the busiest periods, primarily during the Hajj pilgrimage season. Though for centuries before mechanization, the water was drawn entirely by hand bucket, and historical accounts consistently describe it rising close to the surface naturally. The first and most extensively documented scientific puzzle about Zamzam is the aquifer's behavior under extraction. The Hajj pilgrimage now brings between 2 and 3 million people to Mecca each year over approximately 5 days, and the year-round flow of worshippers at the Grand Mosque adds continuous demand on top of that. The Saudi government distributes Zamzam water freely in enormous quantities. Pilgrims drink it, bottle it, and use it throughout their stay. Pumping tests conducted by Saudi authorities and independent researchers in the 1970s and 1980 showed something that required explanation. When the well was pumped continuously at high rates, the water level dropped and then stabilized rather than continuing to fall, suggesting a recharge rate that, while clearly finite, was remarkably sustained relative to what the surrounding geology and climate would straightforwardly predict. Saudi Arabian geologists conducting detailed surveys of the Zamzam aquifer system determined that the water is fed by a fracture-controlled aquifer in the volcanic basement rock, maintained by percolation from the surrounding mountains of the Hejaz region. Mecca is ringed by highlands, and rainwater falling on those highlands percolates slowly through the rock and accumulates in the fracture networks that intersect the well site. This accounts for the general mechanism, but researchers have noted that the recharge rates appear higher than standard hydrological models for the region's rainfall and geology would predict, particularly given that Mecca receives only approximately 80 to 120 millimeters of rain per year on average, with high year-to-year variability. The precise hydraulic model that fully accounts for the observed yields relative to that limited local rainfall has not been published in comprehensive peer-reviewed form, which is what keeps this an open scientific question rather than a closed one. The second and most scientifically significant finding concerns the water's isotopic signature, and this requires a brief explanation of what isotopes in water actually tell scientists. Water molecules contain oxygen and hydrogen atoms that exist as different isotopes, slightly heavier or lighter versions of the same element. And the ratios of these isotopes in any water sample are effectively a fingerprint of where and when that water originated, what climate it fell in, what geological formations it passed through, and roughly how long ago the recharge occurred. Studies examining the stable isotope ratios in Zamzam water, specifically the oxygen-18 to oxygen-16 ratio and the deuterium to protium ratio, both standardized against the Vienna Standard Mean Ocean Water Reference used as the global baseline, produced results that are distinct from the surrounding shallow groundwaters of the Mecca region. The isotopic signature suggests that some portion of the Zamzam water has a significantly longer residence time in the aquifer than nearby surface recharged wells, meaning it has been underground for a considerably longer period before being drawn out. Some analyses have suggested that a component of the Zamzam water may have originated during a climatically different period in the history of the Hejaz region, specifically associated with what researchers call the Green Arabia period. linked to the African humid period approximately 5,000 to 11,000 years ago, when the Arabian Peninsula received significantly more rainfall than it does today and supported vegetation and lakes across what is now desert. This does not mean the water is entirely ancient or static. The aquifer clearly receives modern recharge, as the pumping tests demonstrate, but it suggests a mixing of older, deep-sourced water with more recent recharge, creating an isotopic profile that does not precisely match the local modern hydrological cycle. This kind of mixed isotopic signature is genuinely unusual for a well in this geographic and geological setting, though it is not without parallel in other fracture-controlled aquifer systems around the world. The third area of scientific interest is the water's chemical composition, which has been extensively analyzed by Saudi government laboratories, King Abdulaziz University, and several independent research groups. Zamzam water is notably high in dissolved minerals compared to typical drinking water. It contains approximately 200 to 300 milligrams per liter of calcium, approximately 40 to 50 milligrams per liter of magnesium, fluoride at approximately 0.72 to 0.88 milligrams per liter, sodium at approximately 133 to 170 milligrams per liter, and bicarbonate at approximately 390 to 440 milligrams per liter. The total dissolved solids concentration sits at approximately 600 to 750 milligrams per liter, placing it in the category of moderately mineralized water, noticeably mineral-rich by the standards of typical drinking water, but not at levels considered harmful, and the pH is slightly alkaline at around 7.5 to 7.9. The mineral richness is consistent with the geological origin. Water percolating slowly through fractured volcanic rock over long periods dissolves minerals from the surrounding geology, and the specific mineral profile reflects the geochemistry of the Hejaz volcanic basement. What researchers find more difficult to explain is the consistency and stability of the water's chemical composition over time, despite the enormous variations in extraction rates across different seasons and the differences between high-Hajj season pumping and normal periods. Aquifer chemistry typically shifts somewhat under variable extraction conditions, and the stability of Zamzam's profile across decades of testing is noted in the research literature. Several studies, primarily from researchers at Saudi institutions, have also reported antimicrobial properties in Zamzam water, or unusual resistance to bacterial contamination compared to other water sources stored under similar conditions. The fluoride content at its documented levels is known to have some antimicrobial effect. The elevated mineral content generally can affect microbial growth dynamics, and the slightly alkaline pH may be an additional factor. These are scientifically plausible partial explanations. However, not all of the reported antimicrobial findings have been published in high-impact peer-reviewed journals with robust study designs. Some come from studies with small sample sizes, limited controls, or publication in journals without rigorous independent peer review, and the scientific community outside the immediate research groups has not consistently replicated the strongest claims. What can be stated with confidence is that the water consistently meets or exceeds international drinking water quality standards and has not been associated with documented waterborne disease outbreaks, despite being consumed by millions of people annually under conditions, open distribution, communal cups, varying storage, that would typically create significant contamination risk. A 2011 report by the UK Food Standards Agency found elevated arsenic and nitrate levels in some Zamzam water samples collected from traders in the United Kingdom, which caused concern at the time. But subsequent investigation determined the contamination was associated with improper handling, bottling, and storage by traders outside Saudi Arabia, rather than with the source water itself. The Saudi government maintains strict restrictions on commercial bottling of Zamzam water, precisely because of the contamination risks associated with the uncontrolled supply chain that developed around it. Any honest account of the scientific literature on Zamzam water must also acknowledge that the topic has been significantly contaminated by pseudoscientific claims, most prominently those associated with the Japanese author Masaru Emoto. Emoto claimed that water responds to human intentions and prayers by forming beautiful or ugly crystal structures, and his claims about Zamzam water, suggesting its crystals were uniquely beautiful due to the prayers said over it, were widely circulated in popular religious media across the Muslim world and beyond. Emoto's research methodology was not controlled. His results have never been replicated under controlled conditions, and his theoretical framework has no basis in the physics of water molecules. Mainstream science does not accept his claims about any water source, including Zamzam. The existence of those pseudoscientific claims makes it more important to accurately characterize what the legitimate scientific findings actually show, not less, because the genuine scientific puzzles about Zamzam are interesting enough to stand entirely on their own without embellishment. To be precise about where the science actually stands, the general aquifer mechanism is explained. The elevated mineral content is explained by the volcanic geology. The slightly alkaline pH is explained by bicarbonate-rich rock interaction. And the well's historical continuity across thousands of years is confirmed by the archaeological and textual record. What is partially explained is the sustained yield under extreme extraction. The fracture network and recharge mechanisms are identified, but a comprehensive hydraulic model fully accounting for observed yields relative to local rainfall has not been published. What remains genuinely unclear is the precise contribution of ancient versus modern water to the isotopic signature, whether any antimicrobial properties exist beyond what the mineral and fluoride content would predict, and whether there are hydrological pathways connecting Zamzam to more distant water sources that have not yet been identified or mapped. A well that has served millions of people continuously for approximately 3,500 to 4,000 years, in one of the most arid environments on Earth, with an isotopic signature that does not fully match the local modern water cycle, and a sustained yield that exceeds straightforward predictions. That is a genuinely unusual hydrogeological system that the scientific literature acknowledges has not been fully explained. The honest scientific position is not that Zamzam is miraculous and not that it is completely ordinary. It is that it is a well with verified unusual properties, some of which are explained, some of which are partially explained, and some of which are still active research questions. If you want to go deeper into another ancient system, where the scientific findings turned out to be far more complicated than the textbook version suggested, one, where DNA research completely rewrote what scientists thought they understood, that video is already there waiting, and what it shows will genuinely change how you think about human history.